So the type of experiment we're doing in lab today has a name. It's called calorimetry. Calorimetry, which is measuring calories. Calories are units of energy, so we're measuring energy. Well, we've got thermometers that measure temperature, but we don't have any cool little gauges that can just say how much energy something has in it. And so what we do is we use a container, a calorimeter, and ours is really fancy. It's a styrofoam cup, just like you buy at the grocery store, styrofoam cup. But styrofoam is a pretty good insulator. The calorimeter is a container that insulates what's inside from the outside. And we've got little pieces of cardboard, very fancy again, to use as a lid on top. And what we're going to do is we're going to put some cold water, well, it's really room temperature water. We're going to put some room temperature water in here. And we know its mass. And we know the initial temperature of it because we'll use a thermometer and measure that. We know the specific heat capacity of water, and that is 1.00 calories per gram degree Celsius. We used joules in in lecture. We're going to use calories today. So 1.00 calories per gram degree Celsius. So if we don't do anything to that water, it's pretty much just going to sit at the same temperature. But what if we put something hot into it? What if we took a piece of metal, just like a lump of metal, and it was hot, and then we stuck it in the cold water? What would happen? It would heat up the water, and the lump of metal would cool down, wouldn't it? There would be a flow of energy. Heat would flow from the hot metal to the cold water. And they would end up being at the same temperature at the end, because the heat will flow until the temperatures are the same. So we have a piece of metal, and we can measure the mass of that. We can measure the initial temperature of that. Well, what are we trying to calculate here? Perhaps we don't know what this metal is, so we can't look up its specific heat capacity. We could calculate the specific heat capacity doing an experiment like this. So we have two initial temperatures that are different, and at the end, these are going to end up both being at the same final temperature. So the water's going to heat up, and the metal's going to cool down. So the metal is losing energy. If money leaves your wallet, is that a positive thing or a negative thing? Negative. If money comes into your wallet, that's positive, right? So if energy leaves the system, it's negative. If energy comes in, it's positive. The energy lost by the energy for the metal is going to be a negative number, because what's going to happen is we've got M and we've got C for the metal, and then we have delta T, which is that final temperature, minus the initial temperature. Well, for the hot metal, is the final temperature higher or lower than the initial? It's going to be lower. And so this number here is going to be, not negative 1, that's going to be negative. So Q for the metal is going to be a negative number. We really shouldn't say minus Q, that's confusing. So this is negative. Q for the water is going to be positive. It's the temperature change that tells us the sign. If the temperature goes up, the final temperature is higher, you subtract a lower number and you get a positive temperature change. So Q for the, wow, that got really big. Oh wow. Q for the water is going to be positive. Well, conservation of energy tells us that energy cannot be created or destroyed. So the energy of this system must be constant. We're just transferring energy from one thing to another. And so this heat thing has to be Q for the water plus Q for the metal. Those add up to 0. One of them's positive, one of them's negative. The energy went from the metal to the water, but the sum of those energy transfers is 0. That's what the law of conservation of energy says. So if we're trying to calculate the specific heat for the metal, we can use that relationship, because what that means is that, sorry, wrong color. Q for 1 equals the negative of the other. So that's pretty important right there. Kind of hidden in the middle of all that mess. The energy lost by one has to equal the energy gained by the other. So when we do an experiment like this, we measure the temperature of the cold water and its mass, and we measure the temperature of the hot metal and its mass, and then we measure the final temperature. And so we can calculate the heat gained by the water using the mass, the initial temperature, the final temperature, and the specific heat capacity of water. That gives us Q. Okay, if we want to calculate the specific heat of the metal, this C right here, we need to know these two temperatures, which we know. We need the mass, and we need Q. How do we get Q? Well, we just slap a negative sign on front of the Q we just calculated from the water. So that's kind of the big idea of what we're going to do today. We're going to do it once with hot water and cold water, and then we're also going to do it with hot metal and cold water.